Hello, welcome to today's class. This would be our fourth class on logical agent, and in today's class we will talk about how to perform inference when using propositional logic. And in today's class we will perform inference using model checking. In the previous class we have looked at the syntax and semantics of propositional logic, and we also have talked about what a knowledge base is. So a knowledge base consists of sentences that represent the rules and fact. And in the last class, we created the knowledge base for the Wampus game in using propositional logic. So we have introduced the rules of Wampus game in one of the earlier class. The knowledge base that we created in the previous class in propositional logic is something like this. So we had 5 sentences in the knowledge base. 3 of the sentence came from the rules of the Wampus game, and the last 2 sentences came from the percept that the agent has perceived so far. The first sentence says that there is no pit in square 1 1 because the agent started in square 1 1, and as per the rule of the game there is no pit in square 1 1. So this particular fact can be represented using this sentence in propositional logic. The second sentence is for the rule which says that square 1 1 will have breeze if and only if there is a pit in square 1 2 or square 2 1. So from this rule of the game we can construct this sentence in propositional logic. The third sentence comes from the rule which says that square 2 1 will have breeze if and only if there is a pit in square 1 1 or square 2 2 or square 3 1, because these 3 squares are adjacent to the square 2 1. The next sentence says that there is no breeze in square 1 1, and the last sentence says that there is no breeze in square 2 1. So our knowledge base have 5 propositional logic sentences, and let us give a name to each of the sentence. So let us call the 5 sentences by the name R1, R2, R3, R4 and R5. Now we want to perform inference. Inference means we want to find out whether the knowledge base entails some sentence alpha or not. So for example, we may be interested to know if not of P12 is entailed by our knowledge base or not. So not of P12 means there is no pit in square 1 2. And now in today's class we will perform the inference by using an algorithm called model checking. Model checking also we have studied in one of the earlier class, and how model checking works is it enumerate all the models and check whether alpha is true in every model in which KB is true. So in all the models where the KB is true, alpha also has to be true. Then only we can say that KB entails alpha. And we also know what we mean by a model. So model are assignments of true or false to every proposition symbols. Now, in case of the knowledge base that we have created, there are 7 proposition symbols. They are B11, B21, P11, P12, P21, P22 and P31. It will be more clear if you look at the knowledge base. So the knowledge base is listed here, and as you can see we have 7 different proposition symbols in this knowledge base. Now, since we have 7 proposition symbols, the total number of models will be 2 to the power 7, which is 128. So we can create 128 different models. This slide shows the 128 different models that we can create. Of course, it doesn't list all of them. It's a partial list. So here we have the 7 proposition symbols 1, 2, 3, 4, 5, 6, 7. And now we can have 128 rows. So in the first row, all the proposition symbols are false. In the next row, all the propositional symbols except P31 is false. P31 is true here. Similarly, we can continue and create 128 different models. Now this table also shows what is the truth value of each sentence in the knowledge base. So for the first model, R1 is true, R2 is true, R3 is true, R4 is true, R5 is false. So how did we calculate this value of these sentences? The value of these sentences are calculated based on the semantics of propositional logic, and we studied that in the previous class. Now the knowledge base will be true for a particular model. That means in a particular row, the knowledge base will be true if all the sentences in the knowledge base is true. So for the first model, that means in the first row, all the sentences are not true. R5 is false. Since all the sentences are not true, our knowledge base is false. As you can see, our knowledge base will be true only when all the sentences are true for the given model. And actually, if you try out, you will see that out of the 128 different models that we have, the knowledge base will be true in only 3 of the models. And those 3 models are listed here in this table. So these 3 rows, these 3 models, our knowledge base will be true, and for all other models, the knowledge base will be false. So the knowledge base is true in 3 of the 128 models. Now we want to perform inference. As we said in model checking, we will enumerate all the possible models, and that has been done here in this table. We have enumerated all the 128 models. Of course, some of them are not shown here, but we have enumerated all the 128 different possible models. And now if you want to find out whether our knowledge base entails, for example, not of P12, so we want to find out whether our knowledge base entails not of P12. Now, our knowledge base will entail not of P12 only if in all the three models where the knowledge base is true, not of P12 also has to be true. Not of P12 has to be true in all the three rows here. So where is not of P12? This is P of 12. P of 12 is false in all the three, which means not of P12 will be true in all the three models where the knowledge base is true. And hence we can say that not of P12 can be entailed from the knowledge base. So we can infer not of P12 from the knowledge base, and meaning of not of P12 means there is no pit in square 12. So given the knowledge base, we can make this inference that there is no pit in square 12. And please note that we are making this inference by using propositional logic and using model checking as the inference algorithm. I would also like to mention that not of P12 may be true in some other models where knowledge base is false. That does not affect the entailment. So not of P12 may be true in some other models where the knowledge base is false. Only requirement is that for all the models where the knowledge base is true, your alpha also has to be true. The sentence that we are trying to infer also has to be true. Now, let us check whether we can also infer P22. So P22 is here, and P22 is true only for two of the models. P22 is not true for all the models where the knowledge base is true. For example, in this row, KB is true, but P22 is false. So now we can say that the knowledge base do not entail P22. So we cannot say that there is no pit. So we cannot say that there is pit in square 22. So this is how inference can be done in proposition logic using the model checking algorithm. So now if we have to write a program, we have to enumerate all these models, 128 models. So we need to write an algorithm for that. And after enumerating all the models, you have to check whether KB is true or not in those models. And if KB is true, we have to check whether alpha is true or not. So here is the algorithm to do that. So here's the main function, TT entails, and the input to this function is our knowledge base and the sentence alpha that we want to entail. And the function will return either true or false. So if we can entail alpha from KB, the function will return true. And if we cannot entail alpha from KB, and this function will return false. Now the algorithm maintains, so here the two inputs, KB, it's mentioned that KB is the knowledge base, and alpha. Alpha is a sentence in propositional logic. And then now what this function do is it creates the list of proposition symbols from the knowledge base and the sentence alpha. If you remember in our example, we had 7 proposition symbols. So those proposition list of proposition symbol is created in this line of the pseudocode. And after that we call this function check all, and to check all we send the knowledge base, the sentence alpha, and this list of symbols that we created, and a empty set. This empty set represents the model. So right now our model is empty. Now what in this function check all, what we do is we check whether the list of symbol is empty or not. Initially the list of symbol will not be empty, so we'll come to this else part, and this else part we take the first symbol from the list of symbols, and then we remove that first symbol from the list of symbol and preserve the rest, and then we recursively call check all again. We call it 2 times, and first time we assign true value to the first proposition symbol, and in the second one we assign the false value to the proposition symbol. Remember, we need to assign all possible values to each proposition symbol. So we need to assign both true and false to each proposition symbol, and in the first call we are assigning true and false to the first proposition symbol, and then we recursively call check all, and we send the rest of the symbols as our new list of symbol, and we increment our model. In the first call we will increment the model to include p equal to true, and in the second recursive call we will increment model to include p equal to false, and whatever value is returned by check all, we do an AND between those two and we return it to main call. So it may not be very obvious at the first attempt how this recursive function will work. So let us look at using one example, and if you follow this example you may apply this technique to understand other recursive functions also. So first let us say that we have a knowledge base where we have only 2 proposition symbols A and B, and we have this sentence alpha that we want to entail, and alpha have only 1 proposition symbol C. So we want to find out whether KB entails alpha or not. So in this algorithm, if you see, we first create a list of proposition symbols from KB and alpha. So if we create the list of symbols, the list of symbol will be A, B and C. So we have 3 symbols. The first 2 comes from the knowledge base, the last comes from the sentence alpha. Now in the first call we take the first of symbols. So the first element from symbols is A, so we assign that to variable P, and the rest of the symbols, so when we say rest of symbols it means B and C, that we'll assign to this variable called rest. and then we are calling check all 2 times. For the first time we will assign p equal to true, so a will be assigned the value true, and in the second recursive call p will be assigned the value false, so a will be, or p is equal to a, so a will be equal to false, and we will increment model to include a equal to true and a equal to false. So for this call our model will be, a partial model that we are creating will be a equal to true, and for this call our model will be a equal to false. And as we make the recursive call we pass the value of rest. So rest is bc, so we will pass bc and we will pass bc, and for the second recursive call this rest, the value of rest will be taken by these variable symbols. So in the second recursive call our symbols will be equal to bc, and for this recursive call our symbol will be bc. So we have called this function again, so we need to evaluate it. So this is the recursive call. So this is the recursive call, and we need to see what will happen for this call. So in this call our list of symbol is bc, and since this list of symbol is not empty, we will go to the else part, and in else part we will take the first of the symbol. So first of the symbol this time is b. For this call first of the symbol is b, and the rest from this list is c. These two lines we are executing for this recursive call. We are executing these two lines. So in the second call p will be b and the rest will be c. Similarly here also p will be b and rest will be c. Of course we will come to this only after this function, this recursive call should finish first, then only we'll come here, although I am showing it together. First this will be complete. When this function call is complete, then we will call a second time, and then only this will be evaluated. Please note that one. And now for the second recursive call, from the second recursive call we again call check. So we are calling check all one more time, and the second time that we are calling we will now pass we will increment our model to include p equal to true. So here p was b, so we will, earlier our model was a equal to t, now we will increment this model a equal to true, and to this model we will add b equal to true in the first call, and in the second call we will add b equal to false. So as you can see our model is getting created one by one proposition symbol at a time. First we create the partial model where a was true, and now we are creating the model a through b through, then a true b false, and whatever was the value of rest we pass it during the call, which will be taken by the variable symbol. So in this second level our symbol will be equal to c, and here symbol will be equal to c. Now as we we call this recursive call again, and now we have to perform this function for this call. So first thing we do is check whether symbol is empty or not. So symbol is not empty, it has the element c. If it is so, then I'll go to else part, and from this list of symbol I will take the first symbol. So the first symbol will be c, and now p will be equal to c, and if we remove c from this list of symbol, our variable rest will become an empty list. Same thing will happen for this call also, but remember we will perform this call only after finishing this call. uh, so now we are calling uh, now once we calculate the value of p and rest, next we will call check all, one more recursive call. And this time uh, as we call, we will increment our model to include p equal to true and p equal to false. So this time p was c, so we will increment our model. So here the model was a true, b true, then we will include c true, and we'll also include c false. So we have created the model a equal to true, b equal to true, c equal to true, a equal to true, b equal to true, c equal to false. However, as we called it for the third time, this time our list of symbol is empty. So when we check whether our list of symbol is empty, it will be true. So we will no longer go to the else. For this call, we will not go to the else. Instead, we will come to this part, and here we do with this PL true means we will evaluate. See, we are evaluating the knowledge base in the model. So this is our model. The model is A equal to true, B equal to true, C equal to true. So in this model, we will evaluate our knowledge base. That's the meaning of this function, PL dash true. So we will evaluate the knowledge base in this model, and if it is true, then you remember what was the meaning of entailment. If the knowledge base is true, then alpha also has to be true. So if knowledge base is true, then we check whether alpha is true or not. Otherwise, if knowledge base is not true, then we don't have to check whether alpha is true or not. So when knowledge base is true, then if if alpha is also true, then we will return true. Else if alpha is false, then we will return false, which means alpha cannot be entailed. If we return false, it would mean that we cannot entail alpha from the knowledge base. However, if knowledge base is true and alpha is also true, we will return true from this call. But entailment is not yet complete. We have to check for the other model also. At least for this model where knowledge base is true, alpha is also true, so we will return back true. So the first thing is to check whether the knowledge base is true here, and if it is true, then we check whether alpha is true or not. So, and if that condition is satisfied, we will return true from this particular call. We will return true from this particular call, and if it is true, we will return true from this particular call also. And since both are true, from this call we will return true. Okay, so this for this recursive call, both the call returned true, so I can return true from here, because here, as you can see in this part of the code, this is end. So the first call also has to be true, the second call also has to be true, then only we will return true. And this end means actually for the first model also it was true, and for the second model also it was true. What is true? We were checking that if knowledge base is true, alpha is true or not. If the knowledge base is true and alpha is also true, we return true. If knowledge base is true, alpha is false, we will return false because it is the end. And if knowledge base is false, then definitely we will return true. We don't have to check whether alpha is true or false. And that particular checking is done here in this line of the code. Okay, so we have assumed that in this example, KB will, if KB is true, then alpha is true, and both the call it returned true, and hence true was returned here. But our algorithm is not yet complete. We have to follow this path now. So for this call, again, this was our partial model, and this time P is equal to C. So we will increment this partial model to include C equal to true and C equal to false. So our model becomes A equal to true, B equal to false, C equal to true, and then A equal to true, B equal to false, C equal to false. And then we will evaluate our knowledge base on this model. If the knowledge base is true, we will check whether alpha is true or not. If knowledge base is false, we don't have to check alpha. Same thing will happen for this model also. And let us say the return value for this call is true and the return value for this call is also true. And since both of them are true, this call will return true. And now for this call, since both the recursive call returns true, this recursive call will return true to the parent. So this part of the tree has been evaluated, but we are still left with proceeding on this direction. And as we try to proceed in this direction, our partial model was A equal to false and our P was equal to B. So now if we make a recursive call, this value B will be added to the model, and hence our model will become A equal to false, B equal to true, A equal to false, B equal to false. And this rest will be passed as the new list symbol. So list of symbol will be C, and as we execute the code, this time P will be equal to C because the first element of the symbol list is C, and once we remove C from the list, rest will become empty. And now if we make a recursive call, as we will make a recursive call, we will add C to the partial model. So our model will be, we have added C equal to true and C equal to false. So our model will be A false, B true, C true, A false, B true, C false. And our list of symbol will become empty. And once list of symbol becomes empty, we will perform this evaluation of the knowledge base and alpha. And let's say this part of the code will evaluate true for both the model, which means for this recursive call, both the call return true. So true and true will be true. So true will be returned by this recursive call to its parent. True will be returned. But we have not yet performed this call. So now we have to perform this call, processing for this call. And as you can see, P was equal to C. So as we make a recursive call, we will add C to the partial model, and hence our model will become A equal to false, B equal to false, C equal to true, A equal to false, B equal to false, C equal to false. And since rest was an empty list here, symbol will be also empty list, because whatever we pass along the rest will be taken by symbol. Rest is the third argument here, and here also symbol is the third argument. So what you pass from rest will be taken by symbols. So our list of symbol will be empty, and since for this recursive call symbol list is empty, so we'll perform this evaluation, and let's say this evaluates to true, and let's say this call also evaluates to true. So for this recursive call, this call was true and this call is also true, so true and true is true, so we will return true to its parent. And now for this recursive call, this call return true, this call return true, so true and true is true, so we'll return true to its parent. And now for this call, the main call, both the recursive call, this recursive call and this one, both are returning true, so it will return true. Sorry. So it will return true to the main whoever called. And this return true means your KB entails alpha, because this logic was satisfied that if knowledge base is true, then alpha was also true, and if knowledge base is false, it doesn't matter. Alpha may be true, may not be true. So this is how the algorithm will work. I hope this illustration helps you to understand how this algorithm will work. And so this was the whole this is the whole, like, how the recursive calls are made. So this shows the flow. So first we'll call here, we'll make this call, from this call we'll make this, from here we'll call this, it will return true, then I'll call this, it will return true. Since both are true, we will return true, and then we'll call this, and for this call we'll call this first. If it returns true, then call here. If it returns true, both are true, so we'll return true. So for this call, both are true, so we'll return true, and then we'll come here, we'll make this call, and for this call we will for this call we'll first call this one, and then from this call we will make this call. Let's say this evaluates to true, and then we will go back and then we'll return the value, and then we'll call and we'll make a recursive call again, and let's say this also evaluates to true, so he will return true back to whoever called this function. And since for this recursive call both true is written for both, it will return back true, and this is how it will progress the algorithm. And this is the algorithm again. Now this algorithm is sound because it implements directly the definition of entailment. So it creates all the models and check all the models one by one. So only the sentences which can be entailed will be entailed. Other sentences will not be entailed. So the algorithm is sound. The algorithm is also complete because it works for any knowledge base in alpha, and it will always terminate because our truth table is finite. So since the truth table is finite, we will be able to enumerate all the models and do the checking. So algorithm is complete. So if it is entailed, then definitely you'll find out that it is entailed. Now if knowledge base in alpha contains n symbols, then there will be 2 to the power n models. You already know this, because if we have 7 propositional symbols, then the total number of models was 2 to the power 7. In the same way, if you have n symbols, then it will be 2 to the power n models. Thus the time complexity of the algorithm is big O 2 to the power n. The space complexity is big O of n because we go in a depth first order. So we proceed along one path, Once we complete the path, then only we proceed to the next path. So the space complexity is big O of n. Now propositional entailment is co-NP complete. So from your algorithms class, you know what is co-NP complete. So NP is a non-deterministic polynomial, which means it is the set of problems for which you can verify if a solution exists or not in polynomial time. You cannot find the solution in polynomial time, but if the solution is given to you, you can verify it in polynomial time. So those are the NP problems, and co-NP is like a problem will be in co-NP if the complement of the problem is in NP. And co-NP complete means a problem will be a co-NP complete if all the other problems in co-NP can be reduced to the problem in polynomial time. So these things you may have studied in details in the algorithms class. And now your propositional entailment is co-NP complete, which means it is a difficult problem. And so every known inference algorithm for propositional logic has a worst case complexity that is exponential in the size of the input. So finding out whether a knowledge base entails alpha if we are using propositional logic is co-NP complete. So whatever problem is in this set, co-NP completes are usually difficult problems. So with that, we'll stop for today's class. We will meet again in the next class. Thank you. Bye.